Today, the shortage of fossil fuel is becoming more and more apparent. Due to its clean emission profile, ease of use, and many other benefits, biodiesel is quickly becoming one of the fastest growing alternative fuels in the world. With a minor subsidy, biodiesel can be as cheap as petroleum and has become the fuel of preference for millions. This clean, renewable, and cost-effective source of energy can help ease the depletion of petroleum, providing economic and environmental benefits well into the 21st century. Using used vegetable oil from our school cafeteria, we were able to produce biodiesel through base catalyzed transesterification. We were able to predict the amount of biodiesel that could potentially be produced each month from used cooking oil discarded by the school. This in turn has allowed us to determine the amount of electricity that could be saved if we were to burn this biodiesel in an electric generator. This video will discuss our experimental design and procedure in making the biodiesel, then delve into the calculations for how much electricity we could potentially save with this type of fuel.
So the first step of our experiment is to obtain cooking oil, which is provided by Long, a supervisor from our school cafeteria. So here is our unprocessed oil. As you can see, it is very dark and full of particles at the moment. You will need to clean this oil beforehand in order for the transesterification reaction to be successful.
The cooking oil from the cafeteria, we now have the materials for our projects. But first we have to clean the oil, which can be done by removing small particles using a coffee filter and the funnel.
To quicken the process, it is recommended to also heat the oil, which makes it less viscous and easier to filter. Additionally, we're going to filter it 2 times, which will ensure that all of the particles are removed in the process.
In order for a transesterification reaction to occur, we need to first neutralize the acidic cooking oil that we have. To do so, we're going to perform a standard titration to determine the amount of sodium hydroxide required.
First, take 1 milliliter of oil and 10 milliliters of isopropyl alcohol and mix them together, which will create our test reference. Then, make a 0.1% aqueous solution of sodium hydroxide using 0.5 grams of sodium hydroxide pellets and 500 milliliters of distilled water. Perform a titration test on a small sample of oil by adding sodium hydroxide drop by drop, keeping track of how much you use. Once we have calculated the amount of sodium hydroxide required for a titration, we can now begin the transesterification reaction. Mix together 220 milliliters of methanol, 6.95 grams of sodium hydroxide, and 1 liter of filtered oil in a plastic bottle and shake the bottle for 5 minutes. This will enable the triglycerides to react with methanol, creating fatty acid methyl esters and glycerol in the process. Then, store the plastic bottle in a fridge overnight, which will give enough time for 2 separate layers to form.
Once 24 hours have passed, take the bottle out of the fridge, and now we can see 2 distinct layers. The one on the top is the biodiesel solution, and the one on the bottom is the glycerol. Remove the top layer only, and place it in another plastic bottle. Now we need to clean the biodiesel we have. The residual catalyst in the solution can be removed by adding distilled water, tilting the bottle up and down slowly, then discarding the water. Do this until the water added into the biodiesel is cleared.
At the end of the biodiesel production process, we were able to create 870 milliliters of biodiesel from 1 liter of used cooking oil. Now we are going to test the energy content of the biodiesel through a calorimetry test. First, take 100 milliliters of biodiesel and add it to a spirit burner, making sure that the wick is saturated with biodiesel. Then, set up a tripod with a gauze and place a beaker with 100 milliliters of water on it. With a lighter, light the wick and measure the temperature change of water. Through our calorimetry experiment, we were able to determine the energy content of our biodiesel to be 17.8 megajoules per liter, which is 47% of the theoretical value at 32.8 megajoules per liter. Using the theoretical energy content of biodiesel, we are able to calculate the amount of electricity we can produce with a diesel generator at our school. We can produce approximately 1,250 liters of biodiesel using oil from the school cafeteria in a year, which translates into 41,375 megajoules of energy. With the maximum diesel generator efficiency of 57%, we can produce roughly 6,560 kilowatt-hour of electricity. This can reduce our school electricity cost by 4,170 RMB in a year.
However, if the school were able to attain many times more oil, say the waste oil from the local area, then the conversion process can be executed on a much larger scale. Increasing economies of scale can be achieved and more oil can be produced at a cheaper price. Biodiesel out of cooking oil is no rocket science. With proper chemicals and lab tools, virtually anyone, even a student, can make it. This is why we believe recycling of cooking oil can be easily integrated into our normal high school routine in both classes and clubs.
This will result in three major benefits. First of all, this will reduce the cost of electricity and disposal of oil. Secondly, it will teach the students the importance of recycling and reusing by producing a form of bioenergy. Lastly, it is a fun experiment that any students interested in science can enjoy.
We believe that the creation of biodiesel would lead to a positive chain reaction. It will raise awareness for biofuel, leading to more innovative and practical solutions to environmental sustainability.